Okay, now that we have introduced the typical sets and the asymptotic equipartition property, we can see an immediate application of these concepts to the problem of data compression. Again, data compression. So we can prove the same result of data compression, so we can compress data in a lossless way down to the entropy of the source using a completely different idea, no Kraft inequality, nothing of what we have seen before, simply using asymptotic equipartition property. So how do we do this? Well, we can do the following. We can prove that there exists a fixed to variable lossless source code of sufficiently large block length n such that the compression rate, so the average length divided by n, is less than the entropy plus a quantity that becomes as small as we want. Of course, we know that for example, using Kraft inequality, well, we have that this lower bound. So at the end, this proves the existence of codes that can, in fact, work as close as we want to the entropy. How do we do this? Well, we can simply consider the following. For large n, the source is going to produce with overwhelmingly large probability a typical sequence. So we can simply index all the typical sequences. So we simply associate indices to all the sequences in the typical set using how many bits? Well, we know that the size of this set is upper bounded by, the size of t is upper bounded by 2 to the n times entropy plus some delta epsilon. So we need basically just the ceiling function of the logarithm of this quantity. So we need these many bits to uniquely index all the typical sequences. Then what happens if the source by accident produces something that is non-typical? Well, in this case, we simply just represent all the source without compression. So we need simply n times log of the cardinality of the alphabet ceiling function, and this will be what we need in terms of binary symbols. Okay, and then we prefix the typical sequences with a 0, the non-typical sequences with a 1, so we know what's going on. If the decoder sees a 0, then it reads the index and goes into the library of typical sequences and takes the sequence corresponding to the index. If it sees a 1, then it takes the whole sequence explicitly. Okay. So then we can compute the average length, and the average length we divide. We have these many bits for the typical sequences, these many bits for the non-typical sequences, and then we average over all typical sequences here and all non-typical sequences here. Then we simply collect terms, and we end up with something that is in fact dominated by n times the entropy, and then we have terms that as we divide by n, either they go to 0 as 1 over n, like for example in here, or they are multiplied by epsilon, and this epsilon can be made as small as we want. So the overall thing here, the overall penalty term here, can be made small by taking small epsilon and large n. So this shows the existence of codes that can compress arbitrarily close to the entropy. And as you see, the style of the proof is completely different from what we have seen before. Okay, that's another way of proving that achieving compression rates as close as we want to the entropy is possible. Okay, but this is not our main goal here. We want to build more tools, and so we are going to generalize the notion of typical sequences to the notion of jointly typical sequences. So now we consider pairs of sequences, x and y, on this Cartesian product alphabet. So this is all the pairs of sequences where x is over the alphabet x, y is over the alphabet y. And we can define, the joint empirical distribution as simply this the set of empirical frequencies for every pair of letters xy. We count the occurrences of the pairs of letters xy in the pair of sequences. We divide by n, and those are the empirical frequency of the pairs. And we can define the jointly typical set as all the pairs of sequences xy such that their joint empirical frequencies are close to the true joint probabilities, exactly the same way. So the definition is completely symmetric with respect to the individual typical sequences. Now we have some more properties of the jointly typical set. In fact, it's easy to prove, and you will do this as a homework. So, by the way, this week I will not give exercises because we are just building tools. There will be more exercises for the topics of next week. So you are supposed to do these proofs by yourself. And for what I have done before, it's relatively easy to work in the same way, basically, and get these results. So what we can prove is that for the jointly typical set with respect to a certain joint distribution, we have that if x and y are jointly typical, then x is individually typical with respect to the marginal distribution x, y is individually typical with respect to the marginal distribution y, and we have the asymptotic equipartition property, so the probability the joint probability of x and y is exponentially equivalent to 2 to the minus n times the joint entropy, which means, in fact, that p x n y n of x y is in between 2 to the minus n times joint entropy minus some delta of epsilon and 2 to the minus n joint entropy plus some delta of epsilon. Okay, this is proven in the same way as before, directly from the definition of jointly typical set. Then, of course, property number 3 is a direct consequence of property number 1, because if x and y are individually typical, then their individual probabilities also satisfy their own equipartition property. And probably number 4 is maybe the only slightly different property to prove here, which says that also the conditional probability of x given y or conditional probability of y given x are asymptotically exponentially equivalent to 2 to the minus and the conditional entropies. So homework, prove this one. Okay, it's not difficult, just from what you have, it's very easy to show it. Okay, size of the conditional typical set. So what is the conditional typical set? Well, let's take a given sequence x in xn, given, and then I can ask, I can define the set of all the y's such that the pair xy is jointly typical. So this is a set over y. This is a subset over yn. Is a subset of yn. Okay, and I call this set the conditional typical set given a fixed sequence x. Okay, and it turns out the proof is completely symmetric to what we have seen before, that the size of this conditionally typical set is upper bounded by 2 to the n times the conditional entropy of y given x plus some delta. Okay, again, homework, do this. Here another lemma, which is a bit more complicated to be proven, and therefore we do it explicitly, is the so-called conditional typicality lemma that says the following. So first of all, the idea is the following. Suppose that I take an x typical. In this case, x is given and it can be anything. X can be anything. In particular, if I take x non-typical, well, then there will be no pairs of xy that is jointly typical, because a condition of being jointly typical is to be individually typical from property number 1. So if I take a sequence X that is non-typical, then this conditional typical set is empty. But of course, empty also satisfies this upper bound because 0 is less or equal than this exponential. But now I'm interested in doing a different thing. I take a typical X. And what is the probability that a sequence Y generated according to the conditional distribution given that specific X is jointly typical with X? And it turns out that this probability tends to 1. So we have this result as n goes to infinity. As a technicality, to make the proof simple, I have to consider a slightly more restrictive condition on X. So X is not just epsilon typical. X is convenient to take X epsilon prime typical, where epsilon prime is a bit more restrictive than epsilon. Okay? So this is epsilon prime, and this is epsilon. And this makes the proof quite easy. At the end, it doesn't really matter, because those epsilon and epsilon prime are arbitrary positive quantities, and then for sufficiently large n, this probability will become arbitrarily close to 1, independently of how we pick this epsilon and epsilon prime. As long as this must be, in order to make the proof easy, we use this restriction. Okay. So here I give the proof explicitly because it's a little bit more complicated. The proof goes as follows. So we pick an epsilon prime typical sequence X, and then given X, we generate, a conditional distribution for Y, which is a product distribution where the terms are these conditional probabilities. So we generate Y conditionally on X. And then we look at the condition for being jointly typical. So the generated Y to be jointly typical with X. And in fact, we want to show that the probability that this generated Y is not jointly typical goes to 0. So instead of showing that it is jointly typical goes to 1, we show it the complement event that is not jointly typical goes to 0. And what does it mean is not jointly typical? Well, it's not jointly typical means that for some letters X and Y, for some, the corresponding empirical probability is farther apart from the joint probability by more than epsilon times the joint probability. So if for some X and Y this inequality holds, then the sequence Y is not jointly typical with the sequence X. Then we take the union over all possible pairs X and Y, and then the probability of this union event, it means that for at least you know, for a few, it could be one pair x and y, it could be two, so it's the union over all possible. If this probability goes to 0, then we know that for all x and y, the empirical frequencies are close to the true probabilities, and then the sequence y is jointly typical with x. Okay, so we do as follows: we pick letter x, and we pick it such that the individual probability px is positive, because if it's 0, it never appears, and therefore we don't really care. This letter will never appear, and so we can exclude this case from this union, because this will be an event of measure 0. Okay, so without loss of generality, we pick a letter that can appear with positive probability, and then we consider this probability, the probability that you know, this is a union, right? So every time we have a probability of a union, and we want to show that this probability of a union goes to 0, well, we can use the union bound. So we prove we write the probability of a union of events is less or equal than the sum over the probabilities of the individual events. If we can show that each one of those goes to 0, and we have a finite number of events, so this sum is finite, well, then we can prove that the union goes to 0 if each individual probability of these events go to 0. So here we consider a specific pair x and y. We pick an x, and then we fix x and y, and we look at the probability here. The probability, you see that the empirical frequency is deviates from the true probability by more than epsilon times the probability. And if we can prove that this goes to 0 for every x and y, we are done by the union bound argument. Okay. So what we do? Well, we first of all we divide everything by px. That's why we have to we take px greater than 0, because we can divide everything by px. In this division makes sense. We cannot divide by 0. So what happens when we divide the joint probability by px? Well, the joint probability, remember, the joint probability px comma y divided by px gives me py given x. So we have it here and here. Then we multiply and divide this term. Oopsie, what happens? We multiply and divide this term by the individual empirical frequency of the letter x in the sequence x. And then we collect the terms in this way. We take, basically, this is just rearranging the terms, so we can collect, you know, these two terms here, and then these two terms here, okay? This is just rearranging the terms in this product, and dividing everything by the conditional probability of y given x. So now we have, again, absolute value greater than epsilon means the union of two conditions, the value greater than epsilon and the value smaller than minus epsilon. So those conditions are disjoint, because, you know, something is, imagine we are considering, this is epsilon, this is minus epsilon, and we are considering this region and this region. So the probability of these disjoint events is the sum of the probabilities. In any case, we could we can use the union bound. So the union of these is less or equal than the sum of the two. And so when we take the condition greater than plus epsilon, and we carry the minus 1 on the other side, oopsie, we have this event. So we have the probability of this plus the probability of the other event, which follows by taking the minus epsilon, carry the minus on the other side, and flipping everything. Okay. So at this point, we have to consider each one of these probabilities, and if we can show that each of these two probabilities goes to zero, the sum goes to zero, then the individual term goes to zero, and then by the union bound, we have proven that the probability of the union goes to zero. So what we do, now we use the fact that, and here is where this assumption is useful, that the sequence X is epsilon prime typical, which means that its individual frequency is in between 1 minus epsilon prime times the true probability and 1 plus epsilon prime times the true probability. So this ratio is bounded by these two values, okay? So what we can do, we can simply, if we increase this factor by replacing the bound 1 plus epsilon prime, then we make this event bigger, and so we get an upper bound, then this will be the upper bound, okay? And if we decrease this factor by by replacing it with the lower bound 1 minus epsilon prime, we make this event also bigger because the inequality goes in the other direction, and therefore we also have an upper bound here, okay? So we have these two upper bound, and now we notice that these ratios 1 plus epsilon divided by 1 plus epsilon prime is greater than 1 because epsilon prime is smaller than epsilon, and 1 minus epsilon divided by 1 minus epsilon prime is smaller than 1, again because epsilon prime is smaller than epsilon. Therefore, we have this, right? But in addition, since y is generated according to this conditional distribution, it turns out that by the law of large numbers, what happens is that the ratio of the joint empirical probability and the individual empirical probability tends in probability, so it converges to the conditional distribution, okay? So now what happens is that it means that you see these terms, where is it? These term here, actually I should write it here. This term and this term, which is the same, converges to something that is P of y given x. Y given x. So we have P of something that converges to Py given x greater than a quantity larger than 1 divided by multiplied by the same quantity, P of y given x. So the probability of this is it tends to 0 because this quantity converges here, and this is always greater than this quantity. So the probability that this random variable is larger than what we have here goes to 0 because at some point the term to the right is always larger than the term to the left, and vice versa. Here the same. This converges to Py given x, y given x, and this term is less than 1. So now we have that we have this quantity less than something that is less than 1, and therefore again the probability that this becomes bigger is vanishes. Okay, so okay, so basically this shows that both these two probability goes to 0, and then we work backward. The individual probability of the individual event for a fixed pair x and y is 0. We sum over all. There are only a finite number of x and y's, and therefore by the union bound we have proven that this probability goes to 0. Okay. Yeah. Good. So, okay, this concludes the proof. what is the consequence? A consequence of this conditional typicality lemma is that we can also provide a lower bound on the size of the conditionally typical set. So this corollary says that taking epsilon and epsilon prime in this order, and for all epsilon prime typical x and sufficiently large n, we have that the size of the conditional typical set y given x is larger or equal than 1 minus epsilon times 2 to the conditional entropy minus delta. And the proof of this follows very, very closely the same idea of the proof of the lower bound of the, where is it? Wait a second. Oh, it's much before the proof of the lower bound of the cardinality of the individually typical set. So the proof of this result. Okay. When you see the proof here, you can basically replicate this proof. What I did here. But of course now we have to use the fact that this conditional probability goes to 1, which is the conditional typicality lemma that we have just proved. Okay, so the bottom line is that also for the conditional typical set, we have that if x is epsilon prime typical, and we take epsilon greater than epsilon prime greater than 0, for sufficiently large n, the cardinality of the conditionally epsilon typical set on y, this is a subset of all the y's that are jointly typical with x, is exponentially given by 2 to the n times the conditional entropy. Okay? So the intuitive visualization of this is the following. Imagine that we take all possible sequences x and we list them like this in lexicographic order. Generally, there are 2 to the n log cardinality of the alphabet x sequences. And on the other side, we take all possible sequences y, and we put them here. Now, it turns out that only a few of these x's are individually typical. We have seen before, we indicate them with these arrows. Some of the sequences, in fact, an exponentially smaller set of cardinality 2 to the n times the entropy, are individually typical with respect to the distribution px, so the marginal distribution, and some of the sequences y that I indicate here are individually typical with respect to the marginal distribution py, and those are 2 to the n times the entropy of y. Then it turns out that some of these pairs are also jointly typical, and those are indicated by, let's say, by those dots. You see, not all possible pairs of individually typical sequences are jointly typical. Only a few of them. For example, this pair, if I take this one here, there is no dot. It means that these y and these x are individually typical, but they are not jointly typical. And why we know that there are less? Because we know that the joint entropy in general is less than the sum of the two entropies, which means that the size of the jointly typical set, which is 2 to the n times the joint entropy is generally less than the product of the sizes of the two individually typical sets. So if all pairs were let's say, individually typical pairs were also jointly typical, it means that the joint entropy is equal to the sum of the entropies. It means that x and y are independent. But generally, x and y are not independent. For a general joint distribution, they are statistically dependent, and therefore the jointly typical set is smaller than the Cartesian product of the individually typical sets. Okay? And then, for every typical sequence x, there is, for example, for this one, there is a set of sequences y which are jointly typical with that specific x, and this is precisely this conditionally typical set y given a specific x, and so happen for y. If I pick an individually typical sequence y, there will be a set of sequences x that is jointly typical with that specific y, and this has the size of 2 to the n times the conditional entropy. Okay, so this is a good picture to remember. A good picture to remember. To give you an example, I want to, just to be even more clear, I want to give you an example of a distribution for which we can easily see that individually typical and jointly typical means something very different, and that's why there are generally much less jointly typical sequences than all possible pairs of individually typical sequences. Suppose, for example, the following distribution so we take x and y, they're both binary. So x is 0, 1, y is also 0, 1, and I consider the following joint distribution that associated pxy, say 0, 0 equal to 1/2, and pxy 1, 1 also equal to 1/2. Okay? So, and of course, the probability of 0, 1 and 1, 0 are 0. Okay, that's a little bit of an extreme case, but okay. So what do we expect to see for individually typical sequences? Well, if I marginalize, so this table is basically I have 0, 0 is here, 1, 1 is here, then I have 0, 0. When I compute the marginal in one direction, I get 1/2, 1/2. When I compute the marginal in the other direction, I have 1/2, 1/2. So individually typical sequences are sequences that have the same proportion of roughly the same proportion of zeros and ones. So for example, I can have a sequence x equal to, I don't know, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, something like this, where 50% zeros and 50% ones. And then I can have an individually typical y, for example, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0. Okay. And those can be individually typical because their empirical rate of zeros and ones are close to 50%, because so they're close to the corresponding individual marginal probabilities. But we see immediately that this sequence cannot be jointly typical. If I consider the pairs xy, I see here that I have many instances in which I have, for example, 0, 1 appearing, 0, 1 appearing, 1, 0 appearing. Okay, so clearly we see from the joint distribution that 0, 1 and 1, 0 can never appear together, right? So a jointly typical x and y would look more or something like, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0. You will never see 0, 1, and 1, 0. Okay, so this already shows you that individually typical and jointly typical means very, very different. Jointly typical are those sequences that have the joint empirical frequencies close to the true distribution. Okay, that's why here in general we have this condition, right? We have this condition, which means not all pairs of individually typical sequences are also jointly typical. That's a very important fact that we will see the significance later. And the other idea that this chart visualizes is the following. We have seen before with this conditionally typical set that if I pick a typical X, there exists a subset of Y's that are jointly typical with X. So this is the subset that we have defined, are all the sequence Y in the alphabet, over the alphabet Y, such that X and Y are jointly typical. Okay. This is the conditionally typical set that can be seen as follows. It's given a typical X, we have a subset of Y's that somehow are strongly related with, to X and the others are not. And the size of this subset is the conditional entropy. So we have that the size of the typical set with respect to Y is 2 exponentially 2 to the n times the entropy. The size of this conditional typical set is 2 to the n times the conditional entropy. And we also know that conditioning reduces entropy. So in general, this exponent is bigger than this exponent. So this is a subset. Okay? Good. So we can move on and introduce, further generalize to, for example, triples of random variables. So if we have XYZ with a certain joint PMF, we can, of course, define the jointly typical set in exactly the same way. We always refer to the property that the empirical joint frequency for every XYZ is close to the true joint probability. So then you can generalize this to any vector, right? You can define, for example, the typical set of any set of random variables is always the refer to the joint distribution, the joint PMF of that random variable. And in particular here we have this additional property which is very close the proof follows closely the proof of the conditional typicality lemma that we have seen before, and you can do it as a homework. It's a little bit more difficult, but okay, this course is difficult. So this proof says the following. Suppose that we have a triple of random variables x, y, z that forms a Markov chain. Forming a Markov chain, I repeat, because I already said that a couple of times, means that if I condition with respect to y, x and z become conditionally independent. Or, in other words, equivalently, that the joint PMF of XYZ can be factored as PX, PY given X, PZ given Y. In other words, in general, by the telescopic rule, here we would put all the variables already appear, so the conditioning should be with respect to x, y, but because it's a Markov chain, the condition with respect to x disappears, because when we condition with respect to y, whatever is to the left of y in the chain is irrelevant. Okay? Good. So it turns out that if we take xy to be epsilon prime jointly typical, and we generate z random according to the conditional distribution of z given y, then the probability that the triple x, y, z is jointly typical goes to 1. So this is the same idea of the conditional typicality lemma, but applied to this Markov chain. Notice that now here we generate z depending only on y. And nevertheless, because x and y are jointly typical, the probability that x, y, z are jointly typical goes to 1, which means that in fact we don't really, we generate z in a way that is completely independent of y. Sorry, the independent of x. The dependency here is only on y, but at the end, because we pick x and y jointly typical, at the end, x, y, and z are jointly typical with high probability. Okay, this is an important property that is used at some point in some proofs, and is a generalization of the jointly typical. The conditional typicality lemma seen before. Okay, well, you can do it by basically replicating the same steps that we have seen before explicitly. One more thing, sometimes I will neglect the conditioning when it is clear from the context. For example, here I say in the text that z is generated according to the conditional distribution z given y for fxy. So to be very precise, I have to put here the conditioning, but what happens in general is that because otherwise the notation becomes very cumbersome, when it is clear from the context, I would simply write this without the conditioning, and it's well, we know from the context that z is generated according to this conditional distribution. Okay. Very good. So I think that we have done quite a bit. We have to prove now 3 very important lemmas. One is called the joint typicality lemma, and then based on joint typicality, we will prove 2 important lemma. One is called the packing lemma, and one is called the covering lemma, and these will be the central tools to prove the channel coding theorem and the source coding theorem. So we see this in the third part of this lecture, because I'm getting a bit tired, and also the video file cannot be too large. So we stop for a moment, and I will finish in the next part.